Hi everyone, we are back, and now we are going to look at how are we going to analyze small data sets, so specifically when n is less than 30. So one of the problems that small data sets presents with us is that we can no longer use our basically our z tables or your z Gaussian distributions. Instead, we have to use what's called a t-table, and it's a function that essentially now varies as a function of nu, which is your number of measurements minus 1. So basically it looks like nu is equal to n minus 1. And this term alpha now is essentially equal to your level of significance, so your confidence interval is equal to 1 minus alpha. Oops, not infinity, alpha. So what you're looking at here, whereas our other function when we're looking at z, we could find the confidence interval by just looking at the integral into the curve. These values that you get from integration, or actually how do we find essentially our confidence interval, you're looking at, in this table, we look at our, again, depending on our number of measurements, you'll find here, depending on your confidence interval here, which is 1 minus alpha, so this would be our 95% confidence interval. This will give you your kind of standard value that gives you that 95% confidence interval. What does that mean? You're actually getting the area from whatever your t value is here, from here to infinity. And this value represents the area from minus infinity to t. So this, if it's a 95% confidence interval, should be 0.95. But if you integrate the area should be what's left over. Let's go ahead and let's kind of look at an example. I think it's always usually better done with an example. So here's my mean, here's my standard deviation. I'm going to calculate my t experimental, and now I can go ahead and look at, I have, for example, 18 measurements. And let's say I want to find my 90% confidence interval. So if I have 18 measurements, that means that my nu is 17. If I want my 90% confidence interval, I'm going to do basically the alpha. Remember, confidence interval is equal to 1 minus alpha. So therefore my alpha is equal to 0.1. So, but I want my confidence interval, so I need to divide that by 2. So I'm going to look at from here to 0.1. I want to do that. Actually, sorry about this. So my confidence interval is here, so my alpha is going to be this. So I don't need my 2 sides. So 2.567. So that is going to be my, I'm looking for that confidence interval there. So let's go ahead and let's see what this gets me. So it should be 2.567. So let's see, where does 95% of my data going to fall? So my student t distribution, I give it the number of, or my degrees of freedom, 17. So my nu value. I could pull out this function here that's a little bit nasty, a little bit unelegant. And now I could go ahead and solve. I could do that right now. Let's solve, because again, 90% of my data is going to fall basically between this minus infinity and whatever that t value is. So I'm going to say t like 90. So I want to say, when does this whole thing, so for example, when does this set equal to 0.9? Solve for t90. So what will be my value? Oh, actually, sorry. Let me abort this evaluation. It's actually, so again, it's 1 minus, so it's going to be basically 0.1. Let's see. Let's see if we can solve for this value. It's taking a little time, but again, the function is not an easy one to work with. So again, just got to make sure that we give it our due diligence. Create our function with respect to x, solve for t90. You may even do numerically solve. Let's abort this evaluation. Let's numerically solve it. Actually, we could try to put this in different. And if this fails, what we'll do is just plug in the number and see how it looks like. So for example, 2.576. It's taking a while. My other computer will run faster. So I could see that value of basically 0.01. So actually, again, this will be because it's 10%. Excuse me. So actually, let's go back. So it's the 10% interval, so 0.01 exactly, because it's 1%, 90% confidence. So we can see that that's giving us that value. So we can see where we'd expect, or we could calculate what are bounds of our t experimental that will put us essentially in that 95% confidence interval. And after that, you can kind of do some hypothesis testing and other things. But we can still set our basically our confidence interval bounds very, 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 very similarly. So again, it's that t alpha over 2 value, and then we could get those and actually calculate those. So that's pretty much what we've got here. So this is excellent. And then the next time we're going to get into some Anova analysis. And again, you can develop error bars based on these confidence intervals. If they overlap, then you'll get those. You'll also see some p-values. P-values are related to t-values, are just p equals 1 minus t. So it's just the other, again, it's what we it's the other area, the side of the curve. So that's it. All right. Next time, Anova analysis, and then we'll be on our way. See you next time. Thanks. Bye.